Okay, um, before I work set D, I want to give you an overview of what we've done so far. Okay, so let's go with average height. That's something that we've worked with a lot. So let's say that we think the average height of students at Emory High is 5'10". So that would be 70 inches. Okay. So we think the average height of men is 70 inches. Okay. So we want to test that theory. To test that theory, we're going to run around and we're going to measure a bunch of kids. But we don't have time or money or whatever to measure all of the kids. So we stand out in front of the school, and the first 144 boys that walk through the door, we measure how tall they are. Okay? And let's say that we measure and we get an X bar, an average of 71.5. It might be, yeah. It could totally be biased because of lots of things, yeah. And let's say the SD is 3 inches. Okay. Katie and Jayla, we paying attention? Are you confused, Jayla? This is chapter 26. Okay. Now, we have to decide how accurate do we want to be? Or rather, instead of choosing our accuracy, we actually choose our inaccuracy. 5%. So we are going to have a confidence level of 5%, which means I am willing to be wrong 5% of the time. Okay, but no more than that. So 1 out of 20 times, this method won't work. Okay, if you want to be more confident, then you change it to 1%. And those are really the only two that we use. So I draw my curve, and I assume that the middle of the curve is 70, right? But when I did my survey, I ended up with 71.5. And I'm hoping that the area to the right of 71.5 is bigger than 5%, right? So my null hypothesis says X bar equals 70. My alternative hypothesis says X bar is greater than 70. Okay? And I'm attempting to prove that 70 is true when I'm willing to be wrong 5% of the time. So I need to calculate an SE. Which SE do I need? SE average. Okay? So the SE average is going to be 3 divided by the square root of 144. So 3 divided by 12. 3 divided by 12. And I get 0.25. Right? So now I need to create a z-score of this according to 0.25. So this is 0.25. How many SEs is it from here to here? 6 of them. 6 quarters, right? So that is a z-score of 6. If I calculate the area from 6 to infinity, what am I going to get? 0.00000. So this is essentially 0. Okay? Do I now believe that the true height of men at Emory High is an average of 70 inches? No. We reject the null and we accept the alternative. Now, can I make a guess at what they really are? I could make a confidence interval and all of that, but I'm pretty sure it's not 70. I think it's bigger than 70. Okay, so just to show you the other way that things can work, let's say I do this survey and I end up with 68.75 as my sample average. Okay, and SD is 8 inches. Okay, so my null is going to be x bar equals 70, and the alternative is going to be x bar is less than 70. Okay, and I want a confidence interval of 5%, which means 1 out of 20 times I will be wrong. Okay, but I'm 95% sure. So I draw my normal curve and I stick my expected value at 70, and then over here I have 68.75, and I want to make sure that this area is larger than 5. Because if that area is larger than 5, I can accept the null hypothesis. So I need to find an SE. Which SE am I using? SE average. So I'm going to take 8 and I'm going to divide it by 12. 8 divided by 12, what is that, 2/3? So the SE equals 0.6 repeating. Okay, now I need a z-score. How far is it from here to here? Negative 1.25. Negative 1.25. And what do I do with negative 1.25? Not yet. I need a z-score. Divide it by 0.6. Repeating. Okay. So negative 1.25 divided by point, lots of sixes. Excuse me. Okay. Negative 1.875. Now I need to find my area. I'm going to shade norm from negative 5 up to negative 1.875. So clear my draws and shade norm from negative 5 to negative 1.875. And I get an area of 3%. It said 0.03. So my area is smaller than 5%, so I reject the null and I say no. We think that 70 is wrong. We think the true average is less than 70. And here's what we say. The average height at Emory High is significantly less than 70 inches. So highly. So let's find one that works. I was hoping this one would work, but it didn't. I just made it up. So let's do one more. Actually, we need all of that stuff gone. No, it didn't work. Okay. So let's say my X bar was 69.5 and my SD was 6. Okay. This one should work. So I put my 70 here. I put my 69.5 here, and I say that my null is X bar equals 70, and my alternative is X bar is less than 70. Okay. And my confidence will be 5%. Okay. So I need an SE average. So I take the 6 and I divide it by 12 and I get 0.5. Everybody get that? And then how far am I from 70? Negative 0.5. So I take my difference, negative 0.5, and I divide it by my SE, which is 0.5, and I get negative 1. So my z-score is negative 1. I now want to shade from negative 5 to negative 1. This one should work, yeah. So negative 5 to negative 1. And I find the area. And it's just going to pop up for a second. 0.158. So this area here is about 16%. Okay? So I accept the null. Is the average height, could the average height of people at Emory High be 70? Yes. And we might be wrong, right? 1 out of 20 times, this method is not going to work. So to use the word significant, we would say this. The height of students at Emory High is not significantly less than 70. Right. So if you accept the alternative, you would say is significantly less than 70. So if you wanted to do highly significant, you would rework this and do 1% instead of 5. Yep. Right. Now, it's kind of weird because the whole point of statistics is to try to delete the null. Right? That's what we're always trying to do. That's what we want, usually. Yeah, if you were doing a drug test, you would give somebody a placebo and somebody a drug, and you hope that the drug does not equal the placebo. Right? So most of the time, we want to reject the null. So being highly significant makes it harder to reject the null. Right? So the goal is to land inside this 5%, most of the time, not always, but most of the time your goal is to land in there. Okay? That way you could see, so this is the placebo and this is the drug. That means the drug worked, right? If we can reject the placebo and accept the drug, that's a good thing. But whenever they do medical tests, they usually do 1%. And then this will be the placebo, and we're hoping to land the drug in there. But it's a lot harder to land in the 1% window than it is to land in the 5% window. So you could say the drug worked significantly better than the placebo did. But what you want to say is the drug was highly significant versus the placebo. Okay? And then this is only the first of several types of tests. All right, set D. We are recording this, right? Yes. I think my mic is on. Okay, 26D. Tests of significance. I'm on page 482. True or false? A highly significant result cannot possibly be due to chance. False. How often is a highly significant result wrong? 1% of the time, right? How often is a significant result wrong? 5% of the time. Okay? If a difference is highly significant, there is less than a 1% chance for the null hypothesis to be right. I think this is a semantics. So go back to 481. Look at the box at the top of 481. The p-value of a test is the chance of getting a big test statistics, assuming the null hypothesis to be right. P is not the chance of the null hypothesis being right. It's the chance of getting a big test statistic. And the answer is false, right? Yeah, so it says, um, no, it's the bottom half of that. P is not the chance of the null hypothesis being right. Right. Yeah. Okay. So you weren't confused. You were just explaining it. Right on. You confused me. Okay. If a difference is highly significant, there is better than a 99% chance for the alternate hypothesis to be right. False. For the same reason. Okay. True or false? If P is 43%, the null hypothesis looks plausible. Yes. Because it's bigger than 5%. Okay. So anytime, it doesn't matter where you're looking, whether you're on this side or whether you're on this side, this is always the null. And then this is always the alternate. So the alternate is either going to be 5% or 1%. So if we end up with 43%, we're smack dab in the middle of the null. Okay? If P is 0.43 of 1%, the null hypothesis looks implausible. So we're less than half of 1%. That would be highly significant, right? Yeah, that would be highly significant. Okay, 3. If the observed significant level is 4%, the result is statistically significant. True. Because most of the time we're trying to land in that window. If the p-value of a test is 1.1%, the result is highly significant. No, it's only significant. It's almost highly significant. It's just a little bit over. If the observed significance level is 3.6, then p equals 3.6. Well, the observed significance is p. It's just, they're the same thing. If z equals 2.3, then the observed value is 2.3 SEs above what is expected on the null hypothesis. True, which would be significant. We would have to shade norm to see if it's highly significant or not. 2.3 might be. It would be close. If we looked up 2.3 in the table, you get points, nope, 0.97, so it's not, that's not high enough. It's just significant. It's not highly. Okay. An investigator draws 250 tickets at random with replacements from a box. What is the chance that the average of the draws will be more than 2 SEs above the average of the box? Now be careful here. So this is our expected value, and we're going to go up 2 SEs. And what is going to be the area of this? It's not 5, it's 2.5. Why is it 2.5? Yeah, because the left side also counts. And that 2SE rule means that there's 95 in the middle, which means there's 2.5 on either side. So, no. So if we use the 2SE from the chart, you get 0.954. Yeah. Yeah, so it's actually if you use the chart instead of the shortcut poster, then this area is 95.4, which means that there is 4.6 in both sides. And if you cut that in half, you get 2.3, and they just said there's not much difference between 2 and 2.3. Yeah. And, are we allowed to round like that? Well, all of these are just guesses anyway, so they're not too concerned. Okay, 100 investigators set out to test the null hypothesis that the average of numbers in a certain box equals 50. Each investigator takes 250 tickets at random with replacement, computes the average of the draws, and does a z-test. The results are plotted in the diagram. Investigator number 1 got a z-statistics of 1.9, which is plotted as the point 1, 1.9. Investigator 2 got 0.8, which is plotted as 2 and 0.8, and so on. Unknown to the investigators, the null hypothesis is true, which means that the average of the box is actually 50, right? So we know that the null is true. They don't. So 100 people did one test each. And you'll notice their answers are somewhere between -2 and 2.6. Do you guys see that? So I have a 0 line, and the people are scattered all over. And the lowest one is -2, and the highest one is like 2.6. Does everybody understand that graph? Okay. Now, there should be just as many people above 1 as there are below 1, correct? Okay. A, true or false, and explain. The z-statistic is positive when the average of the draws is more than 50. Yes. B, how many investigators should get a positive z-statistic? 50 of them, half of them. How many of them should get a z-statistic bigger than 2? Close. It's not 5. It's actually 2.5. Right? So 95% of the people should be within 2 SEs. How many will be above 2 SEs? 5%. Or sorry, half of 5%, 2.5. Okay. How many of them actually do? 3 out of 100, which is really close to 2.5%. So it worked. Okay, and if z equals 2, what is p? We just did that in the last problem. It's 2.3% or 2% or 2.5, right? All of those are so close to each other, they're practically the same.